Okay, for today's class activities, for chapter 27, sections 1 through 3, we're going to go over concept questions 4, 6, 9, and 10, and exercises 11 and 14. And as usual, make sure you read this thoroughly, being very careful to look over the details so that you can use these exercises as application and practicing with the concepts. So concept question 4, go take a look at concept question 4 and try and think what the big idea is with that one. Okay, so the main idea is that in order for current to flow, the electric field needs to be pushing charges in the same direction, and even more so that they need to, if the cross-sectional area of the pipe's all the same, the wire, it needs to be constant throughout. Okay, so for this section of wire, we're assuming it's all the same material and the same cross-sectional area throughout. This charge distribution of surface charges, what kind of electric fields would that cause? And you can see that there's a more positive over here and less here. So inside the wire, we would have a net electric field pointing that way in this region of the wire. And the same can be said over here, only in this direction. And if you look in the middle, this is equal charge here and equal charge here, which means they're going to cancel each other out. The field in the middle will be, we'll have a vector this way and a vector this way of the same size, so we get 0 in the middle. And so if this wire is full of charges, then the electrons, those electrons would want to flow this way here. These want to flow this way here, which would mean they'd pile up here. But that would violate our physical constraint that the charges cannot pile up. They cannot get more dense. The repulsion force between like charges is such that it keeps a uniform density of the sea of electrons that can flow through a conductor. So this cannot work as a viable surface charge pattern that would create an electric field causing a current. And just to build off of that, what would work if this was the charge distribution right here? How would I finish it off? And what would need to happen? So if you notice, from going from here to here, I reduced by 2 charges. And so I have a net of 2 charges pointing this way. So going from here to here, I need to have a reduction of 2 charges again. So I actually want to have no charges at that point. And then what about over here? I don't want to have 2 negative charges. Okay, so from here to here, there's a net of 2. Okay, so basically I could cancel out a couple in terms of their electric fields and have 2 left, positive, giving the electric field this way. Okay, but here I have these 2 and nothing, which gives me an electric field that way. And here I have nothing and 2 negatives, which means electric field points towards them. And so this way I'm getting a constant electric field that then can drive current through it. Okay? So that's how physically a current is driven, by creating an electric field from surface charges that are distributed properly, so the electric field is consistent with the flow of current. And in the case of a uniform cross-sectional area, same material pipe or wire, then the electric field must be constant. It must be constant. Okay, let's go ahead and try 6. Okay, so we have these 4 currents, and you're supposed to rank their magnitudes. Current flows in to this junction here, and then flows out here. How would you rank the currents? What's the main idea? Okay, the biggest idea is that it's the conservation of charge. Because again, whatever comes in must come out. So if current IA is coming into this junction here, that means some of that goes this way and some of that goes this way, which means IA definitely must be bigger than B and C. Now, all that comes together and hits here, and so we have IB coming into this junction, IC coming into this junction, and ID coming out, which means IB plus IC must equal ID. And so IA must equal ID, because whatever came in must come out. And IB and IC are less than either of these. Now, because all the wires are identical, we can take a step further. Everything's identical, which means when current gets to this point, it has an equal probability of going left as it does going right, which means IB and IC are equal to each other. So IA equals ID, and both of those are twice as big as IB, which equals IC. All right? Okay, so 9. Go take a look at 9. All right, so we have this segment of material, the segment of metal, a conductor, that then gets expanded by twice the radius, okay, or at least bigger radius. And current flows into here, and then we're asking, and it's the same material, it just gets bigger. Then we're asking to compare the current here to the current here. Okay, so how do the currents compare? How do I1 compare to I2? Again, the main idea is that charge is conserved. And so the current, whatever current is, how much charge is flowing past a point in some amount of time. And if I have 10 electrons flow into this pipe, 10 electrons better flow out of that pipe, which means that the current is the same. Even though it gets wider, it must flow. Now, the other two questions, like the current density, compare the current densities. Now, from your reading, you read that current density is current divided by area. And so that's saying how much current per unit area is flowing. And that area is a cross-sectional area. So if that's our definition of current density, then which one's bigger, J1 or J2? Okay, we can see that the one with the smaller area has a bigger current density. So this is like that. We have J1 greater than J2. All right, now that kind of makes sense when you think of density. It's how much current, how packed is the current. Well, if I have 10 electrons going through this small pipe, they're a lot more, the amount of charge flowing is more per cross-sectional area. Now, you need to be careful not to think that means the electrons are actually closer together. We're going to see with the next question that it means that they must be going faster here, which means there's more current flowing past this line per unit area than it would flowing past the line in here. Okay, so the last question is compare E1 and E2. So knowing that the current is constant, we need to relate current to electric field, and it is sigma A E. Now sigma is the conductivity. That's all those constants that make up the material. So silver has a certain value for this. A is the cross-sectional area, and E is the driving force. Okay, so we derived this. It's in the text, but it's also we derived it in the video before this lecture. So with that, we can see that E is equal to I over sigma A. And so if the electric field is, if the cross-sectional area is small, the electric field is big. So we have a similar thing of E1 is greater than E2. Okay, and so that E1 being greater than E2 means there's a bigger force on the electrons here, causing them to travel faster than there is in here, thus preserving our basic idea of conservation of charge. Okay, let's move on to 10. Take a look at 10. Okay, so the current in the wire doubles. So we have I equals 2I naught. let's just assume our original current is I naught. And so our current in a wire doubles. What happens to the current density? What happens to the conduction electron density? What happens to the mean time between collisions? And what happens to the electron drift speed? Are each of these doubled, halved, or unchanged? So how do those variables depend on current? All right. So we've already defined J as I over A. So if the current doubled, that means J doubled. Okay, because it's directly proportional. Everything else stayed the same. Okay, the next one is the conduction electron density. Now that's this number N sub E. Okay, so this is the number of electrons per unit volume. That's what that means. Okay. Now, how does that relate to the current? Well, there's current, I should say, is related to this, but this is a fundamental property of the material. This doesn't change unless you change the material. So this is dependent solely on the material, which, since we didn't change the material, that doesn't change. Okay, what about the mean free time? That's the tau that you saw in the derivations. That's the time between collisions, the average time between collisions. How does that depend on the current? Okay, so the tau is also a fundamental property of the material, and so because of that, it doesn't change either. Now, both of these, along with the mass of the electron and the charge of the electron, all come into play into this sigma, which is a property of the material. So these don't change unless you change the material. Okay, finally, what about the drift speed? Okay, so we need to come up with a relationship between current and the drift speed, which you've seen, and it's in the reading. So what is the relationship between current and the drift speed? Drift speed is V sub D. Okay. Now, with a little rearranging of what you saw in the text and in the video, the drift speed, it's defined this way, but we actually found that a little bit earlier in saying that the current is equal to the electron density times the cross-sectional area times the drift speed. So we could first figure out, well, how does the current or the electric field change, knowing that these are all constants? Or we can go back directly to the current and say, well, the current is doubled. This is a material property. It doesn't change. We haven't changed the cross-sectional area of it, which means the velocity must double. Okay, so this didn't say this goes to 2J0, and BD goes to 2VD0. So what's really important with this problem is recognizing there's a ton of variables in the definition of current, a ton of them. Many of them are just constants that are material properties. So many that we just group them all together to be one number. And then there's geometric properties, the A, and then there's active properties, the electric field or the voltage or this drift velocity that are all related to each other. All right, very good. So now let's go on to an exercise. Let's apply these now with some numerical values. Go ahead and look at exercise 11. Okay, so we have this rectangular film, very thin, but we're going to make it look three-dimensional there. Okay, let's go ahead and give it a width. There's the width of it, and current flows like that. Okay, current flows like that, and then it's got a thickness here. I'm going to call it T. That's the thickness of this film. All right, which means this face here, the current's flowing through that face, has an area of thickness times width. Okay. Now, so this problem, it gives you the dimensions of the width and the thickness, and it tells you that the current density is 7.5 times 10 to the 5th amps per meter squared. So how do we then find how much charge would go through the film in 15 minutes. Okay, first of all, I realize we're going to be using time, so I'm going to do something different. I'm going to do an H here. So that's height. So we know J, and we know J is equal to I divided by the area, which means the current is equal to the area times the current density. And the area is just equal to the height times the width times the current, or now current density multiplied by that area. So we have all that. And if we plug in our numbers there that are given out of the text, you'll end up with 1.406. I'll keep enough digits here since this isn't the final answer, times 10 to the negative 4. And this is current. That is coulombs per second, and it has its own symbol, its own SI symbol of amps. So that's the same thing as A equals amps. All right. So I often like to just keep it in terms of coulombs per second because that's a little more fundamental. Okay, so that's the current. That's how much coulombs are flowing past a point in 1 second. So now how do we finish this problem of asking how much charge flows through that film in 15 minutes? How would you do that? Okay, so the idea is that the Q ought to be equal to the current times the change in time. Okay, because we defined current as the amount of charge flowing past a point in some amount of time. And I did a DQ here to map how much has changed, but that's the same thing as a maximum if we're referencing our 0. Okay, so with that, we just need to take this value here and multiply by 15 minutes, only convert that to seconds. Okay, and if we do, we'll end up with the Q being 0.13 coulombs. And that's a lot of charge. So this really small wire having a fairly small current, okay, this is 0.14 milliamps, okay, or 140 microamps. That's pretty small. Yet in 15 minutes, that can deliver a pretty sizable amount of charge. That would be a big amount of charge. Okay, so again, practicing with different definitions and also remembering the physical nature of this. This is a flow of charges, coulombs per second. All right, now let's finally finish off with number 42. Now 42 is a lot like this one. So I want you to really go take this as an example and go try and do 42 and see just how far you can get through it. Okay, so with the picture in 42, we have this plastic film that is rolling up on a roller that's got a radius here. So it's got a radius, and we know that radius. Okay, and we know the width of this. I'm going to give it an L here for that width. And this is rolling up, and we're given an angular speed omega. And it's negatively charged, and we're given a surface charge density. So that would be this eta, this Greek letter eta. It's N with a hanging curve on its front leg. Okay, and so we need to figure out how much charge, how much current do you need in milliamps to plate the, sorry, I'm looking at the wrong one. What is the current moving in the film? So what is I? Okay, so what's the definition of current? What's the fundamental definition of current? We can't jump back here and use some of this because what's moving the charges is not an electric field, it's physical moving. But the definition, just like we saw down here, it's the amount of charge flowing past a point in time. Okay, so we have to rederive an equation for current in this plastic film moving. Okay. Well, first of all, if we choose a length here, call that dx, and this is moving at a linear speed vt, then I could find out how much charge is moving in time by saying, okay, the amount of charge is is this eta times the area over dt. But the area would be the width times the amount, the length of it that moved in this time. And so we can call that the dx. So we have L dx over dt. But what is dx dt? That's our velocity of eta L v sub t. Okay, so now we just need to find Vt, which is related to omega. We know that Vt is equal to r omega. The tangential speed is going to be equal to the angular speed times the radius. That's our definition, converting tangential to angular. And then r omega is given, but it's given in revolutions per second, so we just need to be careful to convert that to radians per second and then multiply it by the r. So if we do that, we have eta L r omega, and now it's all in terms of numbers we know. If you plug that in, we're going to get this current of 7.54 times 10 to the negative 8 coulombs per second. And it's negative because it's negatively charged. We're depositing negative charge there. The second question is, well, how long will it take the roller to accumulate a charge of negative 10 microcoulombs? So that's the same thing as down here, only, and we're solving for time this time. So if I just use this right here, I can say delta t equals the charge I'm looking for, the total charge I'm looking for, divided by the current. So this coulombs divided by coulombs per second gives me seconds. So if I plug in the numbers they give there, the negative 10 microcoulombs, this is going to take 133 seconds. Okay. All right, so that's an appreciable amount of time. This is rotating at 90 RPMs, which is just a little bit, 1.5 revolutions per second, and it's not very big, which means it takes a while for this to wrap up. So this isn't going very fast. And so that takes a healthy amount of time. So that seems reasonable to get this negative 10 microcoulomb charge. All right, so that's the end. Again, a big focus today is on understanding what each variable means and how the relationships are. This question in particular, I wanted to use because it's deriving current from a first principle. We achieved this and other forms like this in the reading and the derivations in the video. The other videos, and that was for understanding what's driving them inside a wire. Well, in this case, it's just static charges stuck to a piece of plastic but moving, but the same idea holds.